Finding the distance you've traveled is easy if velocity is constant, right? If you're traveling at the same speed, then the distance that you've traveled is just velocity times time. But if velocity is varying, it's not easy to find that distance. So you're going to see an example of how we apply Riemann sums here to estimate the distance traveled when the only thing we know is velocity. So for example, suppose the odometer, which measures how far you've traveled, on the car is broken, and we want to estimate the distance that we've traveled over a 30-second time interval. We're going to take speedometer readings every 5 seconds and record them, and we're going to be able to estimate the distance we've traveled based on that. So we want distance in feet, and unfortunately right now we've got a situation where our units don't measure up, right? We want distance in feet. Odometers or speedometers give distance in miles per hour. We also want our time to be in seconds, and right now our time is in hours. So let's make an adjustment here just to do some conversions and get that out of the way so we can change the value of what we've got in our table. So we know that 1 mile per 1 hour would be the same thing as 5,280 feet over 3,600 seconds. So what we're going to do is take that 5,280 over 3,600 and multiply that by each of our values. So 17, for example. And that gives us 24.93. We're estimating, so let's say approximately 25. So what I'm going to do is just replace this with a 25. And then I'm just going to do the same thing with all these other numbers. That's just an example of how you can quickly convert between units. You probably would have had to look up these values to know how many feet are in a mile. You could figure out how many seconds are in an hour. But I'm going to replace these values now with velocities that are not in miles per hour, but feet per second. All right, so now that we've got a table of useful numbers rounded to whole integers, let's graph this data and see what it looks like. So I'm just going to plot each of these points on a graph over time, being my x-axis, in seconds. And that's going to look like this. So each one of these points represents one of those data points from every 5 seconds that I tracked the speed of the car. And notice how this is going to be related to the area problem, right? Just as an example, at 0 seconds, we are traveling at 25 miles per hour. So that would be 25 miles, right? And then 5 seconds later, we're traveling at 31 miles an hour. So if I know how fast I'm traveling at each second, then that's going to tell me how far I've traveled over that second. And I've got it in feet per seconds. So 25 feet per second initially, so 25 feet, plus whatever speed I was traveling after 1 second, and after 2 seconds, 3, 4, and 5 seconds. All of this is going to tell me the distance that I traveled here. So this is where we're going to want to apply a Riemann sum, and we'll use a left-hand approximation here to create a rectangle that'll help us do that. So that'll be our first rectangle that we'll use for our Riemann sum. We also need this area here. So we've got a second rectangle. We've got a third rectangle. Fourth. This one will end up being an over approximation there. And there we go. So we've got 6 rectangles now that are going to help us approximate this. And this is where we're going to want to apply a sum. So since it's a left-hand approximation, we're going to use our general form for these left-hand approximations and just say that the distance is going to be the limit as n approaches infinity of the sum f of t I minus 1, right, because it's a left-hand approximation, times delta t. And that's the sum beginning with the first term through the nth term, because we're letting n approach infinity. And so this is the calculation that we're going to be doing here, which is essentially the limit as n approaches infinity of, and I could start adding together all these terms, right? The first one is going to be f of our initial time times delta t. And then our second one is going to be f of our first time measurement times delta t. And this continues finally, the last term that we're going to add is f of t of n, whatever that ends up being, times delta t. So this would be the best approximation we could possibly make, but we have actual rectangles here, and it's cut up into 6 pieces. So let's calculate our approximation using the data that we actually have. So we're going to say that distance is the sum from our first to our 6th term, because that's how many rectangles we have, of f of t of I minus 1 times delta t. And so what is delta t? That's this distance. So we would say that that's b minus a over n, and in our case that's 30 minus 0, and we have 6 rectangles, so delta t is 5, and that should be consistent in each of our ranges here, which it looks like it is. Okay, so that's going to end up being the sum of the 1st through 6th term, beginning with our I minus 1 term, times 5. So we can in fact remove that 5 from the sum to make this calculation a little bit easier. So let's do that. So that's going to be equal to 5 times the sum of the 1st through 6th terms of this function. Because we're using left-hand approximations, that's why this says I minus 1, not I, because this is our first term, and we're actually beginning with the initial term. All right, so let's do the calculation now. So we've got our first rectangle here, and I'll just write in the measurements. So this is a base of 5 and a height of 25, right, because that's how tall that rectangle was. And then we have a base of 5 and a height of 31. We've got a base of 5 and a height of 35, base of 5, height of 43. And this rectangle is a 5 by 47, and this rectangle is a 5 by 45. So I'm just going to add together all of these values, because that's my f of t sub I minus 1. So the 5s are taken care of, but it's going to be 25 plus 31 plus 35 plus 43 plus 47 plus 45. And when I add all those together and multiply the result by 5, I should get 1,130 feet, which is an approximation. It's not as good as what we would have gotten if we had calculated the limit as n approaches infinity, but we used actual rectangles here, and we're going to end up with something that is either a little bit over or a little bit under, because we've neglected a bunch of space with these 3 rectangles. But this is another example of this happening in a real-world example. And it's important to note that one thing we're being careful of is that these intervals are all the same when we do these. So we know that we are close, but not exact. But one of the things that we're doing to make sure that we're doing this properly is making sure that these intervals are all consistent, all delta t.